Welcome back, apprentice engineers. I'm your chief architect, and you're tuning in to another explainer produced by Forge College. Now, if you've been following along in our blockchain fundamentals track, you know we're right in the middle of our capstone project, implementing secure blockchain structures. In our previous lesson, implementing cryptographic hashes, we basically built our engine, right? We learned exactly how to deterministically scramble data into those nice fixed-size bytes. But, an engine sitting on a workbench isn't a vehicle. So today, we're taking those hashed bytes and assembling them into one of the absolute most elegant, most essential structures in all of Web3, the Merkle tree. Let's dive right in. Here is our technical schematic for today. We're going to kick things off with the cryptographic blueprint, then move into growing the Merkle tree. After that, we'll figure out what to do with the odd node out, tackle generating inclusion proofs, walk through the verification process, and finally, wrap it all up with a final inspection and review.
All right, Section 1, the cryptographic blueprint.
So, remember, we are taking abstract software concepts and grounding them in exact deterministic mechanics. We aren't just writing code today, we are doing precision engineering. At its core, a Merkle tree is simply a structure that organizes hashed data so you can prove a specific piece belongs to a set, using a supercompact chain of sibling hashes instead of the whole dataset. Think of it like this. It's like being able to prove definitively that a specific leaf came from a specific tree without having to chop down the entire forest and drag it into the room.
Now, you might be wondering, why go through all the trouble of building this? Well, because without a Merkle tree, if you wanted to verify that just a single transaction exists in a block, you'd have to download the entire massive dataset. And honestly, it's slow, it's incredibly heavy, and it's just exhausting for the network. But by using an inclusion proof derived from a Merkle tree, that process becomes blindingly fast and lightweight. We're essentially trading all that heavy lifting for sleek, mathematical efficiency.
Section 2. Growing the Merkle tree. Time for some iterative assembly.
Welcome to the assembly line. Now, a really quick reminder for everyone. You absolutely must use the exact deterministic hash API that we validated in the last lesson. No cutting corners, no swapping algorithms halfway through. So how do we actually weld these bytes together? Well, step 1, we serialize the leaves. Step 2, we hash them in pairs. And listen up, because here is the absolute golden rule of the assembly line. The order of concatenation is non-negotiable. It is strictly the left bytes followed by the right bytes. Left, then right, always. If you flip them, you get a completely different hash, and the whole machine breaks. Step 3, we just repeat this pairing and hashing process layer by layer, moving all the way up until we're left with one single ultimate hash. And that, my friends, is your Merkle root.
Okay, moving to Section 3, the odd node out. Let's talk about handling spare parts.
In engineering, things rarely divide perfectly by 2 every single time, right? We have to prepare for the inevitable edge cases. So what actually happens when our perfectly paired machine has a leftover piece? What if a layer has an odd number of nodes? Well, in cryptography, you can't just wing it. Being a free spirit who decides to hash things differently on a Tuesday just because you feel like it, yeah, that literally breaks the entire cryptographic universe. We need strict rules. We need determinism. And here is our incredibly straightforward deterministic rule for that. The odd node policy. If you end up with an odd node at the end of a layer, you simply duplicate it to form a pair, and then you hash that pair together. You're basically cloning the spare part so the machine can keep running smoothly without crashing. It's clean, it's consistent, and it works flawlessly every single time.
Section 4. Generating inclusion proofs. The secret to lightweight verification. Okay, this is where the magic really happens.
Mastering this specific part is what separates a good builder from a truly great architect. As we highlight across all our courses, it's all about proving you have a specific branch without needing the whole tree. Let's define exactly what this proof looks like. An inclusion proof is an ordered list containing a sibling hash plus its position. And please notice that position metadata. It is explicitly marked as left or right. This formatting absolutely has to be unambiguous. You have to include whether the sibling sits on the left or the right, so that someone verifying it can reconstruct the parent hashes entirely blind. Without that position data, they literally won't know which order to concatenate the bytes, and the proof will fail.
Let's visualize how this builds a timeline. To gather your proof pieces, you trace the upward path. First, you start at your target leaf. Next, you grab its sibling's hash. Then you move up one layer to the parent, grab the parent's sibling hash, and you just repeat this sequential climb all the way up to the root. You are essentially collecting cryptographic breadcrumbs that lead directly from your specific piece of data right to the very top of the tree.
Section 5. The verification process. Let's check our work.
We are officially switching gears here from the builder on the factory floor to the verifier checking the final blueprint. How do we prove those breadcrumbs we just collected are real? We run the verification routine. Step 1. Start with the given leaf hash. Step 2. Iteratively hash it with the provided proof siblings. And you have to be super careful here to put the sibling on the correct left or right side, strictly according to that position metadata we talked about. Step 3. Calculate your way up to the top. If your final computed value perfectly matches the known Merkle root, boom, the proof is solid. It's a deterministic rebuild step by step. If even a single bit of the original data was altered, the final root will be completely unrecognizable. No way around it. And finally, Section 6, Final Inspection and Review. Time to pass the unit tests. It is time for the final factory inspection to ensure our component is functionally correct and ready to ship. Looking at our acceptance criteria matrix here, you need to run your tests against different dataset types. For a single leaf, your output should just be the leaf or an empty hash, depending on your specific convention. But for even leaves and odd leaves, your programmatic output absolutely must be a bit-for-bit match against hand-calculated reference roots. And don't forget, you also need to test for tampering. Intentionally alter a sibling hash in your test and make sure your verification routine aggressively returns false.
So what do we need to pack up before we leave the factory today? First, expose a stable API for your Merkle root. Second, export a canonical proof format like JSON or binary so it's fully standardized. And third, keep all your unit tests and reference outputs completely intact. You are absolutely going to need them for our next lesson, integrating digital signatures for transactions, where we're going to take digital signatures and bind them directly to these very roots we just built.
I want to leave you with this final, immovable truth of cryptographic engineering. Determinism is essential. Any divergence at leaf hashing will break your proof verification downstream. If your foundation isn't rock solid, the entire tree just falls over. It has been fantastic guiding you through this build today. To master more of these Web3 blueprints and dive even deeper into these structures, be sure to visit the website forge.college to check out everything we have to offer. Until next time, keep building securely, and I'll see you in the next explainer.